there's a chance for people to come in later if they want, but we'll get started. Welcome everyone. Before we begin, I would like to acknowledge the traditional owners of the land on which we meet today. In my case here at Curtin, they are the Whadjuk people. I recognize their continuing connection to the land, waters and culture, and pay my respects to their elders past, present and emerging. For those who don't know me, I'm Alexander Prent, a research associate at the John de Leyden Center. And besides a little research, the main hat I wear is to coordinate the AuScope Geochemistry Laboratory Network, or AGN in short. The AGN was established in order to address a community-expressed need for greater coordination of geochemistry laboratories in Australia. And the AGN aims to establish a national collaborative network of geochemistry laboratories, with which we can tackle large-scale continental research questions. And an example of that is to support the creation of the Isotopic Atlas of Australia. Now, the AGN project is supported by AuScope through the National Collaborative Research Infrastructure Strategy, NCRIS. And currently, the AGN project team consists of 13 people, and we hope to expand that in the near future. We receive great support from the AuScope headquarters, Tim, Tanya, and Joe, and we work closely together with the Lithodat team of Fabian, Wayne, and Moritz to develop AusGeochem. For this team here, the sky seems to be no limit. And besides the creation of a network, the AGN works to promote the national capability and investment in new infrastructure. We support open data initiatives, professional development, and end-user access to facilities. A lot of our recent efforts have gone into the preservation of legacy data sets and developing of a central repository in the form of AusGeochem. In the last month, we also have been busy with the ARDC grant applications, where we are involved in a data platform bid led by Tim Rowling. We're leading a data partnerships bid by Brent McInnes. And our expert advisory groups are finalizing the metadata templates that we started on a few months ago. Then we're working on 2 papers to be part of a special publication for a journal that we yet have to decide on. There's an AGM webpage under construction. Argon-Argon cross-laboratory calibration proposal is written to be submitted. Then we've set up a YouTube channel to revisit earlier webinars. And the next one will be about terrain chrom by Macquarie University. Now, without further ado, I've had my talk, and now we should go on to the core body of the webinar that will be presented by Professor Andrew Gleadow, Professor Barry Kohn, and Dr. Samuel Boone. They will talk about the Melbourne Thermochronology group. That then is concluded with a demo by Fabian Coleman of AusGeochem. Thanks everyone. I'll hand over to Andy.
Okay, it's my purpose today to give you a brief overview of the Thermochronology group at the University of Melbourne, and particularly the Fission Track group, and to give you some overview of our data resources and sample archives. The Fission Track group at Melbourne was founded in 1970 by Professor John Lovering, who first introduced me to the idea of fission track dating, which I pursued in my PhD studies, and we've been at the University of Melbourne ever since, except for a 10-year period from 89 to 99 when we were at La Trobe University, when I took the chair of geology there. And that was a very important period, and Barry Cohn's going to talk about that in a little while. But there's more to this than just the story of one group. There are actually 3 commercial ventures that have had their origin in some way related to our research group. That's AuScan Systems back in the early 80s, GeoTrack International in the late 80s, and more recently Lithodat. There are also now 3 other laboratories in fission track analysis around Australia at Curtin University, Adelaide, and University of Queensland, with whom we have excellent relations and with whom we look forward to collaborating much more. So it's a network even just within the fission track domain, which is spreading. We've been very fortunate to have substantial research funding over a lot of this period, almost continuously, from the Australian Research Council, from the Australian Institute of Nuclear Science and Engineering, to cover our neutron irradiations, as long as we did those, up to about 2009. And we've also been fortunate to be involved in a number of major research initiatives, starting with a tremendous amount of funding from ESO Australia in 1980, which really made us into a group. That was followed by funding, sort of energy research related funding by NERDC, right through much of the rest of the 80s. Then at La Trobe in the early 90s, we were part of the Australian Geodynamics Cooperative Research Centre that Barry will tell you more about. And then since the late 2000s, we've been involved in the AuScope National Collaborative Research Infrastructure System, and of which the AGN that we're now, the present context, is part of. There have been tremendous technological developments during this time, and also expansion into other related thermochronology methods, argon 4039 and uranium, thorium, helium, but particularly the last 15 years of development of automated fission track systems based on digital microscopy and incorporating laser ablation ICP-MS for uranium-238 measurements has really dramatically expanded the data component of all this. Having these kinds of facilities and resources has meant that a huge number of people have been associated with the group over the years. Some hundreds of people have been associated in some way or other, either as academics or as researchers, as postgraduate students, as visiting collaborators and sabbatical visitors, and a few other categories as well, probably. Too many to show here, but this gives you a little bit of an idea of the flavour of that. We've also been able to, very fortunate to be able to work on every continent on Earth, to do fission track work all around various regions of the world, and that has given us a tremendous lot of collaborative linkages with other researchers elsewhere, and it all of this reflects tremendous opportunities that we've had and we've been able to create. And if you put that combination together of funding plus people plus technology plus opportunity, then you're going to generate an awful lot of data and materials. And that's indeed what we've done. Our mineral separate archive collection has about 20,000, more than 20,000 mineral separates in it. At the peak times, we've been processing about 1,000 rock samples per year, usually a bit less than that, but this generates an awful lot of material. And we keep the mineral separates of interest, particularly apatite, zircon and titanite and a few others, but mostly apatites. And this is the material that is left over after we've prepared our microscope mounts and done the analyses. And these are stored, they've been stored since the 1980s in these custom-made drawers. And together, there are 39 of these drawers, and each one holding about 500 samples. So there's somewhere around 20,000 samples. All of these are logged in a manual ledger, and there's a whole lot of different volumes of these. And every sample can be located by the tray number and the row and column number, and all of those records are there. These have been digitised as well, but we still keep the paper records. The other major physical resource is the actual microscope slide mounts, of which there are similarly somewhere up around 20,000 now, both produced by the external detector method requiring neutron irradiation, and for the last 10 years by laser ablation, which doesn't. And these are stored in these storage cabinets. Each drawer in these cabinets holds 1,000 slides in 10 trays, each with 100 slides in it. And there's 16,000 capacity for 16,000 just in that group. And there's an overflow collection which we store in suspension files in some filing cabinets as well. Again, these are all documented by largely until the last decade by a radiation number, so we know exactly where we can find them, although these records, again, variably filled out by the people doing the analyses and at different stages of digitisation. The sample data falls into three categories: the basic sample metadata, which is linked to the actual Fission track age data, recorded for every grain. There's an age for every grain that's analysed. For many years, we analysed about 20 grains. These days, we'd typically go for 30 or 40 grains because it's relatively easy to do now. And all of the data is summarised there, and the track length data as well is summarised in this way. These are just the bin data summarised in a histogram. But if you look at the actual output from Fast Tracks, the latest version of our Fission track analysis system, this is a file from a 40-grain analysis. It's about 4 megabytes in size. And if you actually printed out the ASCII file here, it would be more than 1,000 pages of text. And there's an incredible amount of information in there, not all of which we are currently making use of. So there's tremendous opportunities to develop new systems to make measurements with new data resources that we don't yet make use of. The volume of data over that 50-year period, I've just tried to estimate the amount of data. Back when I was doing my PhD in the early 70s, I used to make an old IBM punch card for each sample, recording the bare minimum of data to do a Fission track calculation, and that was 64 bytes of data, and that was all. And that was the limit of the technology at the time. Today, we're producing around 2 to 4 megabytes of recorded data per sample, and we're also recording all of the digital imagery, the 3D digital image stacks for every grain of every sample. And that's a further 10 to 20 gigabytes of data for every sample. So the actual analytical data is lost in the noise of these really big data sets. And this sort of trend is reflected in the kinds of storage media that we've used over the years. For many years, we used old 5 1/4 inch floppy disks. And then we went on to the plastic-coated 1.4 megabyte floppy disks, and eventually we had the untold luxury of using zip drives in the late 90s, mid to late 90s, and at 50 megabytes and later 100 megabytes. In the last 15 years, we've been using these large redundant storage disk arrays. We've got essentially 3 of these, and each with about 16 terabytes of storage. And protection against loss, and all of the 32 terabytes of data that we currently have, mostly the digital imagery, is now uploaded to the cloud, which Sam will tell you about in a little while. And with that very brief introduction, showing you these trends, our data is becoming really important, but also these physical collections are vital and have potential applications for many other researchers. So properly curating and archiving those is a very important thing for us. So with that, I'll pass over to Barry Kohn to carry on.
Thanks, Andy. Well, in the 90s, our activities were dominated by the Australian Geodynamics Cooperative Research Centre. This was a partnership between government organisations, universities, and some industry, mineral exploration industry companies. And the idea here was to develop a geodynamic framework for the Australian continent. And there were several programs within the centre. And the one that we were involved in was a Fission track thermotectonic imaging at continental scale. So this was the vision at the time. And when we started this, this work, we had about 700 samples archived in our collection from across Australia. But these also included drill hole samples and samples from sedimentary basins. By the end of 7 years, we had 2,750 records in our database from Australia. And for this program, we only concentrated on crystalline basement regions. So we, and mainly outcrop samples with a few shallow drill hole samples as well. The people who helped us achieve that number of analyses were a number of PhD students, members of our group, but principally Paul O'Sullivan, who was then a research fellow in our group. And the idea here was to develop new tools for integrating large data set and enabling people to visualize it. So these are the different terrains that we worked on, these crystalline terrains, and here you can see the distribution of samples from across Australia. You'll see there's a large concentration towards the southeast and various terrains around Australia to a lesser extent. We didn't go out and collect every sample. We had a number of contributions from Geoscience Australia, from different geological surveys, state surveys, and particularly West Australia, but also we would give us apatite separates from their shrimp samples. And so we put all this together and we basically developed a map of an interpolated images of an apatite fission track map of Australia. Now, this gives you age here and fission track lengths, mean fission track lengths here. But to most geologists, these are not like a shrimp age or an argon age. They're not dating necessarily a discrete geological event because we're dealing basically with a temperature sensitive radiometric technique. So we need to find a way of making what seems to be an intractable data set somehow meaningful to geologists. And so we developed these, now someone's overridden me.
Yep.
Let's go back.
Just start playing it again. Yeah.
Yep, so here we go.
We got to there, yeah.
Okay, so we developed this workflow here where we went from the data through to different aspects of the data which needs to be inverted. It needs to be modeled to make it meaningful. So we developed these workflows for thermal history, denudation, paleotopography, where we could image these particular aspects. And as we move down the flow sheet, we're increasing the uncertainties and we are getting further away from the basic data. So the result was we were able to produce these time slice images. So we've got here 3 images of paleotemperature, and we're looking here at different times in the past. And what we're seeing is the temperature of the rock. Here we're dealing with the top, possibly 3 to 5 kilometers of the upper crust. So we're going back to about 110 degrees, and this is telling us what the temperature of the rocks were at a particular time. And you can see as we progress through time how they're basically cooling. The same with denudation and the same with paleotopography. To probably make this more meaningful, I'm going to show you a quick time movie. Here we're running through time for over the last 300 million years, and we're watching the cooling history from 110 degrees of rocks all around Australia. So I'll play this movie and you'll be able to get an idea of the visualization of this. And so we're running now. You can see the time, the clock's running, and you can see the different movement of the rocks cooling at different parts of Australia. And you'll see that the western part, the old cratons, are fairly cool, whereas the eastern margin is still quite warm as we move into the Mesozoic. And now we're coming down, and you'll see Tasmania is remaining hot all the time. And then as we move into the Cretaceous and we start rifting on the eastern margin, you can see the rocks are starting to cool here. And Tasmania is the last area to cool in Australia as Australia drifts away from Antarctica. And you can see the cooling effect here. So this is the sort of these are 1 million year time slices through our modeling. And the modeling here was facilitated by Rod Brown and Kerry Gallagher, who were both members of our group at different times. And Kerry had been working on genetic algorithms for modeling, and these were pushed in here as well as interpolating the models. So this is the situation as it was about 20 years ago. And I want to emphasize, this was just displaying a vision, and we've got far more data today in our data sets, and also the way we model and the way we interpolate data has changed. But this was the vision as in the year 2000. And you can see other things we could visualize, here, would be to say, let's look at smooth long-term denudation chronologies across an area. And so you can see denudation rates through time over a terrain. First order, varying the heat flow. Either we assume a constant heat flow or use the variable heat flow as we see it today in those different areas. And another way that we used was, in this case, in the snowy mountains of Australia, we're looking across basically a terrain of Paleozoic crystalline terrain, mainly granites, granodiorites. We're looking at here a shaded DEM, a digital elevation model here. And what we're doing here is we've taken all these age elevation profiles and using this shaded DEM together with simple map algebra, together with our Fission track data, we're able to visualize the various tectonic blocks within this area. And we can see the faults here, and we're visualizing basically what's just a granite terrain. And this was facilitated by Simon Cox at CSIRO. And so when we, some of the main outcomes from some of this work were some publications about visualization and using large data sets to make what seems to be an intractable set of data more amenable to geological interpretation. So by the early 2000s, we'd started accumulating these very early rudimentary digital records. And we put these in the FileMaker Pro. Some were in these Excel sheets. And from this database here, we could access records. We could look at irradiations. We could access the mounts on which these were in our collection. And this was basically a script which was derived from that. And so at this time, we realized that if we were to go into collecting large data sets, we needed to change the way we were doing things, because basically we were still doing a very traditional way of collecting data, which was very labor intensive and also involved irradiations, which also took time. And so we moved on then into the next stage, which was basically an ARC linkage proposal, which was funded to develop a fully automatic system where we could actually make good use of rapidly developing technologies in microscopy, computing, and imaging. And we would also be able to change the way we did things. And I should mention that all the data I've shown you, most of that is still available. We still have all the records, we still have the slides, and we still have splits of most of the data. And so with that, I'll move you on to the next chapter and pass you on to Sam Boone.
Thank you very much, Barry. So we're now up to the present, and I'll quickly introduce you to our current research group, as all of our members are currently involved in, to varying degrees, with a lot of the work that I'll be showing you in the subsequent slides. So as Andy and Barry have explained, over a 45-year history, we've accumulated a vast physical and digital data collection. And there's a number of challenges as we move forward. The first of which is we want to essentially create a new organized and queryable digital database for our physical collection. We then want to develop a secure and organized way to store our digital data, and do it in such a way that we can disseminate those large data sets to colleagues at different institutions. And then lastly, and perhaps most importantly, we want to make the wealth of associated thermochronology data that we produce with these from these samples findable, accessible, interoperable, and reusable via the AusGeochem platform. And we want to solve all of these challenges in such a way that we can minimize the amount of times we have to actually handle data within our lab. And we want to do it in a way that it actually enhances our science, giving us new capabilities to produce novel insights about the way our planet operates. So our first step towards addressing these challenges is building an in-house relational database to catalog all of our physical specimen that Andy introduced us to. And this would essentially allow you to, at a few clicks of a mouse, to find any given physical resource within our archive. And we're doing this in such a way that not only are we archiving information about our physical collection, but also about the researchers that are producing data, the projects these samples are associated with, as well as being able to retrieve information about these samples. We're doing this in such a way that we can actually host the database on a server, meaning that you can access the database via the web. And it also means that it's compatible with mobile and tablet apps, which is really important because as we move forward, our aim is to essentially use QR code labels on all of our physical specimens, which would then allow you to use your phone or app to scan that a particular QR code and retrieve information about that sample and other samples associated with it. And to do this, we're minting our entire collection with IGSN numbers, or International Geosample numbers, which give you these QR codes that are unique to each sample. In addition, our database can create and connect with APIs. And this is really critical because the end goal is to connect, essentially marry our physical and digital collections by connecting with the AusGeochem platform directly. Towards addressing some of our challenges with regards to how we store our digital data and disseminate it, as Andy introduced us, or mentioned rather, that we're storing all our wealth of digital data, around 36 terabytes, in these hard drive stacks that sit in our lab. But we're also backing these data up on the cloud, which is great because this helps guard against unforeseen and catastrophic data loss potentially, as well as, and perhaps most importantly, it gives us the capability to actually disseminate these data to outside collaborators by essentially giving them a token that allows them to download individual files or whole folders or give access to the entire project if we so wish. And this is quite critical because a number of new challenges have arisen over the past years, and these new digital capabilities are allowing us to address these. One of these challenges is how we actually train colleagues to perform digital fission track analyses. Traditionally, annually, really, people are coming from all over the world to visit our lab. They spend generally multiple months with us and learn how to prepare samples, capture images, perform analyses, do laser ablation, mass spectrometry. But of course, in the COVID era, this is not currently possible, and it may not be possible for quite a while now. Another challenge doesn't necessarily face, it's not necessarily a challenge that our group faces per se, but other fission track groups around the world are facing issues for those groups that are still performing conventional fission track analysis, which requires neutron irradiation, meaning that you have to send your samples off to nuclear reactors, many of which are now closing, or there are new laws prohibiting in certain countries the transportation of radioactive materials. And getting access to other reactors is becoming increasingly difficult due to geopolitical tensions. And so to address these challenges, we've come up with a new distributed digital fission track analysis stream and a remote training module. The distributed fission track analysis stream, the idea behind that is that geologists who may want to actually have some fission track analyses done, they could send us or other thermochronology labs within Australia, such as those at Adelaide, Curtin, and UQ. They can send this physical specimen to us, and then we can capture the images for them for the grains that they're interested in analyzing. We can perform the laser ablation analyses, and then we can disseminate those data back to them electronically, which we do via MediaFlux, but of course you could do via Cloud Store or Dropbox or a data dissemination tool of your choosing. And then those researchers could, from the comfort of their home or their office, could then perform digital fission track analysis using the Fast Track software. This is really exciting because perhaps for the first time, geologists around the world could potentially perform digital fission track analysis without having any of the required hardware to actually do this, something that has never really been possible before. However, this a new challenge arises, and that is, how do you train these analysts remotely? So to address that, our group's working on a digital fission track training module, which essentially allows or takes researchers through a series of steps and modules where they can learn how to identify fission tracks, and then use the Fast Track software. They can choose their regions of interest, perform automated fission track counting using the software, determine C-axis orientation, measure dpars, as well as measuring confined track lengths. And we're already starting to test and improve upon this module with international collaborators, as well as actually trying out and implementing this distributed fission track analysis stream. And so lastly, I'll talk a little bit about ways in which we're aiming to share these data associated with the samples in our collection via the AusGeochem platform. So as many of you tuning in may know, the AGN is teaming up with Lithodat to build the AusGeochem platform, essentially an open, fair-based and cloud-hosted data platform for Australian-produced geochemistry data from around the globe. And for those of you that are tuning in for the first time, I'd encourage you to check out the AGN's YouTube channel. You can see past webinars there and learn more about the work we're doing, as well as the AusGeochem platform. So our group is working with low-temperature thermochronologists across Australia and with Lithodat as well to build method-specific data models, particularly or namely for fission track analysis, as well as uranium, thorium, helium, so that you can upload and synthesize and extract data of these type from the AusGeochem platform. And we're already, even though it's early days, we're already using this to do some novel science. One of these projects is we're actually working with Australian thermochronologists from across Australia to essentially bring that 2002 regional data set that Barry introduced us to, bring that up to speed, incorporate data from all 4 of the thermochronology labs in Australia. So including the new analyses that have been done since 2002, as well as incorporating apatite helium data, and as well as information from basins, in addition to the basement analyses that we had previously. We're also working on a similar continental scale regional synthesis, looking at the Afro-Arabian Rift system with some other international collaborators. So already, even though it's early days, we're getting to use this new tool to do exciting science. So this is the last slide, and I just want to quickly show you how we envision this new laboratory and analytical workflow to proceed in light of these new developments. So say you return from the field, or perhaps a colleague sends you some information, sends you some samples. We already want to record that information into the AusGeochem platform. And we do that via the AusGeochem front end with easy to use user interface. And once you perform some mineral separation and start mounting things, and you start producing some additional physical resources, we want to store all that information within our in-house database. Using the AusGeochem Open API, we then can retrieve that lithological information we've already put into AusGeochem, because again, we don't want to have to record any single bit of information about any sample more than once. So in this case, we'll look at fission track analyses within our lab. So once we've done some analyses, we would have produced a number of different types of analytical information, including digital fission track analyses, so count data and length data. We would have done some mass spectrometry and obtained some isotope concentrations, which we reduced through iolite. And then in certain cases, we might also perform some microprobe analyses to get some geochemical data. Those data are backed up both locally in our hard drive stacks, which are then also duplicated in our cloud storage. And already, if we wish, we could start sharing some of that information, like the digital image stacks, with collaborators outside of our institution. we're also currently working on a script to essentially automatically upload all of those export data into the AusGeochem database. And then again, we can then share that information to collaborators by giving them access to those data within AusGeochem, or we can also then publish those data sets as DOIs. And to tell you more about AusGeochem and what we can actually do with these types of data once they're in the database, I'll hand you over to Fabian Coleman. Thank you very much.
Well, thanks, Sam. Okay, I'm sharing my screen now. Okay, yeah, thanks for Andy, Barry, and Sam to show already all about the data. What we show now, I will focus on the Australian data we have already in AusGeochem. And as Alex already introduced, AusGeochem, what we do is that we are trying to connect all Australian geochemistry laboratories. And Sam showed already we're having now more actual thermochronology labs here in Australia. We have Stan Glory's group in Adelaide, we have Martin Danizik's group in Curtin, and of course we have Melbourne Uni, and then we have Ranji in Queensland, and they will all join the AusGeochem network and contribute data, so we will increase the thermochronology data produced by Australian labs and display them via the AusGeochem platform. To show quickly a brief introduction into the difference what we do as an AusGeochem platform compared to portals is where there are a lot of portals out there which are great ways to find data, but all this data usually comes from different WMS feeds. That means all the data coming with their own standards, their own formats, the fields of different units. So the approach we do, we're having all data we put in. We have a massive relational database. We store all different kind of data types, but what we do, we standardize them all. We bring all the units together. We make sure all the fields talk to each other, that they all use the same standards, and that they actually can start communicating with each other. And having that system set up, then we are able to do these live cross data analytics, which I will show you in a minute. So yeah, that's an overview of the AFD ages we currently have here in the AusGeochem platform. And I tried to put a live demo in, but to make sure it's not falling apart, I recorded it and I will show you a video. So that's data. We have a lot of data coming from the Melbourne Uni lab, so on the East Coast. So we can change the different views. So if we want to get a quick idea of the topography, we can look here. We see the hillshade. We see all the data here around Sydney. You can go on a point to get the information, like we store the latitude, elevation, name, what method has been used, the age, the grain. And then, of course, it depends what kind of data has been provided by the authors. But all the data which is in there is all getting stored in there. And the nice thing is a reference. Every sample has a reference. You click on it, it brings you automatically to the actual paper. You can download the paper. You can do more reading. So that's a really cool feature. But if you want to do more analytics on the fly with the data within there, we can do a multi-selection. So in that case, we can draw a polygon just across the data we're interested in. That's a transect here from the coast to the hinterland. And then it calculates on the fly. It takes all these points, takes all the values in, and creates, for example, age histogram. The nice thing is you can interact with the data. You can adjust the bin size, depending on what you want to see. As you see, the bin size change massively your spikes. We can do age elevation plots. Every single data point has elevation. So if it's not provided by the authors, what we do is we use an API on a high resolution DM, and we make sure every single sample point has an elevation assigned based on the location, if it's not provided by the author of the studies. And a very nice feature for the Fission track data is we can create these mean track lengths versus age plots on the fly as well. You can adjust your y-axis, your mean track length. And yeah, you can see boomerang plots in some cases, so that's quite nice. As I said, it's really interactive. You can just jump, you can do the same at different areas, or we go down here, select another area. Again, really just the points you're interested in. Creating again mean track length versus age plots. Can adjust. And that's for small areas you're looking in. But of course, we can do the same for larger areas if you want to see if there are any patterns or whatever we can see. So here we just select a large chunk on the east coast of Australia. And all that data is being read out of the database, and on the fly, all these graphs are created. And you can see that there are many more points in there. And again, you can see patterns. And it's not just from one study. Whatever data comes in, all the data can be handled the same way. So there's no differentiation. Yeah, age elevation plots, histogram plots. And we are creating many more. We have a radial plot already ready to go. So there's a lot more plots being developed. We're working together with this expert group. So depending on the request, we will develop more plots. And the nice thing is, as I said, because all the data is together, we can combine it with different kind of data. Let's say we put in all the geochron data for an area on top of the fission track data. And again, you just select an area you're interested in. And that's what I said is difference to a portal. You can start analyzing it across different data types. So in that case, it takes all these different data types and creates a plot on the fly. It compares all the data, reads it in. Again, elevation are assigned to all these different data types, for example, and it creates an age elevation plot. And we can spin that further. We can then create multi-thermal chronometers, etc. So that's, I think, to give you an idea what we can do, and there will be many more functionalities coming in future. But I think it's a really powerful tool to give you a quick idea. All these graphs you can export as SVG files. You can then edit them and get them ready for publication. The other nice thing is that's an area here in Alaska where we have some data from William Craddock, a paper they published with a lot of details. You can see we have here uranium, chlorine, DPAR provided. And the nice thing is we store all data. So for each sample, we also store all single grain information if it's provided. So for example, you click on a sample point, then you can also get a age distribution histogram for single grain data. It's also calculated on the fly. Same for age versus DPAR. All your mean track lengths can be in there, and you can export them all. So you have all parameters there. If you want to remodel a sample, you can just download the files, and yeah, you can rerun your models. What we're aiming for now in the future is we want to create these dashboards. So one board where you have then a table of all your selected data. You can decide which graph you want to look at. So you can use pull-down menus. You can swap graphs for other graphs. And I think that will be really nice to then visualize your data and give you a compact understanding of the area you're trying to investigate. And another thing is we're using that on Lithosurfer on our platform, but which is free for the whole academic community, is we are digitizing all these different types of thermal histories. And the labs here in Australia, like the Melbourne lab and Sam and his PhD students, they have already helped us digitizing a lot large data sets. Plus, Dane Glory in Adelaide provided a lot of digitized thermal histories from the Tian Shan mountain. So what we do is standardize them, and they're all digitized and stored in one data table. And then the nice thing is you can then analyze it and looking at patterns. For example, we can query a time. So if we query a time, let's say 100 MAs, here you can see on the lower right a schematic graphic of a foreland basin and the hinterland. And we see these, let's say 100 MAs, there is heating happening to that sample in the foreland basin, and in the hinterland we have asymmetric cooling. But now we want to see, okay, what happened 50 MAs? So we type 50 MAs in. And on the fly in the database, these values are calculated, the thermal gradients, and can be displayed by scales on the map. So for example, we have an interface in the map. That's the data provided from Tian Shan, from Stain's group. let's say 50 MAs, you get all the information on the top right, what model has been used, what the temperature is at the time you're looking at the thermal gradient as a temperature gradient. And you see on the graph on the bottom where you are. Then you type in 100 MAs and it calculates it on the fly and displays it based on the magnitude. So that's something we provide as well. And I think it's a very powerful tool then to look at patterns in a region. Okay, so yeah, that's all for my side. There's much more to come, so stay tuned. And I'm passing back to Andy.
Thanks, Fabian. I think it only remains, if anyone wants to ask any questions, the chat is there. But it's lovely to see so many familiar names in the participants list. And it's lovely that all of you from around the world could join us at probably terrible hours of the day. But anyway, it's very good that you did. I thought that some of you might do it on the recording later, but it's lovely to see you. Yeah. So if anyone has questions, we can, I don't know if Alex, if you've been monitoring.
We haven't had any questions yet in the chat. There is, we're recording this webinar, so if your colleague want to have a look at the webinar, then please visit the YouTube channel. You can put that into the chat. There's also the recordings of the first and the second webinar.
Okay, so I guess if there are no questions, thank. Okay, so I guess if there are no questions, thank you very much for joining us.
Oh, I have a question, Andy.
Yep. Okay. Yep.
Could you put a dollar value on the collection that you have in terms of if you had to start from scratch and put it together, what it would be worth?
Well, many millions of dollars, tens of millions probably. I know that the funding we had from the AGCRC during the 90s, where we processed, well, a part of that was reanalyzing older data, but we reprocessed probably getting up to a couple of thousand samples, maybe 1,500 new samples. Anyway, it took us 7 years and it cost about $1 million to do in 1990s dollars. So, you know, that would be worth an awful lot more now. And if you go back over I guess the research funding we've had over that period is probably somewhere between 10 and $20 million, and that's the output from it. So if you had to go and collect it all again, that would be it. Yeah.
I think we need to emphasize, Andy, that what we have now we regard as critical research infrastructure. This is the basis on which many more things can be done, and it exists, and we're making it accessible. So we view this as research infrastructure, and that is part of what AusScope is about.
Yeah, and both the the properly curated and archived physical collections. I mean, if somebody wants to work on uranium lead in apatites, for example, you know, we're the place to come. and many of the other fission track labs around the world are drowning in apatite samples. So there are a tremendous lot of things that could be done which were different to the original purpose. I mentioned just the sheer amount of data that is not immediately accessible that Fast Tracks produces. If you wanted to actually look at the location of every single fission track within a grain or within a whole collection of grains, that is all recorded. It's like a micro GIS system that has the physical locations to the micron of every fission track that is analysed and counted. And that means that there are new approaches that could be done to look for statistical variations in uranium concentration, which is not obvious to the eye. and not obvious to the user, but you might be able to tell that there is actual heterogeneities in uranium distribution that can be detected statistically. And some, Rich Ketchum is working on developing just such a proposal. So we've got a sort of a rich data format now, an expanded advanced data format that you can export from Fast Track's version 3 that enables you to get all of that kind of extra data. Now we don't yet know how useful that's going to be. We don't really know how useful it is going to be to get a consistent dpar and dper value on every fission track that is ever measured. This is something way beyond the very simple sampling that has been undertaken in the past with manual measurements. So I'm just really looking forward to the exciting things that could be done with people around the world having clever ideas and wanting some data to test them on. This system should provide for it. And of course, although the AGN is Australian based and that's our primary focus is the Australian data set, all of our other data sets are going up, as Sam indicated as well, from those various parts of the world eventually. And of course, other groups around the world are also putting their data sets into Lithodat, so that this will be a fantastic basis for going in and doing the next generation of work. One other thing, when you see the Australian data collection plotted on a map where each point is about 50 kilometres in diameter, in reality, it looks like an awful lot of data. But when you get down on the ground, even that sort of, several thousand data points across the continent, the average spacing of those is of the order of 40 kilometres or so, and it's much denser in some parts of the continent than in others. But there is an awful lot of really interesting geology going on out there that we haven't begun to address with these legacy data sets. So I think there's an incredibly exciting time ahead, and I just wish I was 30 years younger.
Just to add to what Andy mentioned, with that Australian, those images I showed you, as I mentioned, that was done 20 years ago. It didn't have a lot of things in it which we could put in now. And we smoothed a lot of those interpolations. Like we never showed you what happens when you go across a fault. And there's various ways you can deal with that, but we didn't do it. But we could. We've got everything there. So these things can be upgraded, and we can add new forms of data which we never collected with that data set. And that would change things quite a lot. But the fact is that the infrastructure is there, which we can do.
And the more advanced the automated systems become, the easier it will be to go back over some of those legacy slide collections, for example. There's no reason we couldn't go back and reanalyze many of those old slide mounts and collect modern generation fission track data.
I think we have some exciting times ahead of us. And with that, I think we should close this meeting today. Thanks for the presenters. Great job, everyone. And let's see you and others in 4 or 5 weeks with the 4th webinar on terrain chron from Macquarie University.
Thank you, everyone.
Good afternoon, everyone.
Thanks, Alex. See ya.
See you all. Bye. Take care.